Yeah, I think we're already live, right? No? Yes. You never know. You
Anyway,
never know.
hello, hi everyone.
Yeah. Hi, everyone. I think we're live. Definitely. Yes. Hello. So we already. I just joined and start. I noticed that Andrey and Kirk already started arguing about good and bad properties of index health, right?
Started
So
designing
de-
system.
designing. Yeah. Last time we suddenly started working on very like core stuff for btree indexes merge because there is split but there is no merge. We also learned that Andrey's PhD is in the area of indexes and he remembers all the authors and uh, years of papers from 70s even, right? No?
Everything was discovered in 70s.
Yeah,
Actually,
that's cool.
everything was discovered in churches and libraries 1,000 years ago, and we are just re-implementing same
That's
techniques in hardware.
yeah, like principles of life, right? Yeah.
Well, you guys understand the old mainframes used to run something called MVS. It stood for multiple virtual systems. So they could actually run multiple operating systems on the same hardware. I want you guys to ask if Amazon maybe stumbled into that, if maybe that's how Kubernetes, I mean, come on, guys, it's the same solution over and over again, from the 50s and 60s still. So, yeah.
Yeah. Cool. So I when I connected, I heard the question from Andrei why index bloat is bad, right?
I really want to know. I don't
Yeah.
understand.
Let's
Like,
do this. Okay.
let me define what we are working on. So you have a
Mhm.
btree with almost empty leaf pages. And you have a similar btree with deleted leaf pages. Why the second one is better than the first? I don't get it.
Can I answer? Number of block reads required. So let's assume our case. Let's assume we have a 90% deletion happened, right? And let's assume that it was a 1 gigabyte, okay, index. Now I have to read all 1 gigabyte of that index instead of reading 90% less if all of those deleted pages were gone. So just an index scan takes longer, and the number of reads in between takes longer. So,
Mhm.
not only that, next up, you do get the height of the index changes, but we've already agreed we're not going to focus on that for now. Because why? Because the height of the index is a function of the 2 to the power of n. So the reality is you're adding one or two page reads to get to the details. The challenge is when you're reading a 90% empty block, or worse, a bunch of empty blocks, right?
Mhm.
When you're having to spin through those to find the, even if you have a limit of 100 on, right? Let's assume that you can store 80 or 100 items normally on a page. And all of a sudden, your limit 100 would take 2 pages normally. Your limit 100 with 90% wasted space now ends up taking 20 pages worth of reads to get your answer to.
Okay,
Well,
So
I'm not.
let me rephrase.
Let's. Okay. I'm letting you rephrase.
Bloated index consumes more from shared buffers.
Exactly. Pollutes shared buffers.
mhm.
I got it. So, okay, I
Also,
believe
also,
I.
hold on. Let's amplify the problem. I'm not concerned about search speed. We know btree. It's each node has a lot of children, right? So the logarithm, like m in logarithm, is quite working quite well. So we have not a lot of hops, even if we deal with billions of records. The main concern is uh, much more pages. I see 90 plus bloat very often. People love to implement queue-like workloads in Postgres, not thinking about MVCC. Like we have some row, let's update it a few times and then delete it. And this row has a lot of JSON fields or just one huge JSON field. So each update carries this burden, and then updates, deletes, they produce a lot of dead tuples. Auto vacuum doesn't catch up. Also, X-min horizon is stuck a little bit sometimes, and we have bloat. And those pages are not like this space in those pages is not reused. This is this bloat that won't be eliminated by its own on its own. So we need actually reindex. So why is it bad? Pollution of shared buffers, number one thing. Just cache efficiency drops, right?
Mhm.
Second thing, every time we have update, which is not hot, this index needs to be updated, right?
Mhm.
And since each page holds fewer pointers to live tuples, we need to write more pages to wall, full page write after each checkpoint, right? It puts pressure. It puts pressure on replication, right?
So you make full page images for hints, and it consumes wall LSNs.
Yes, yes. Moreover, this is for replication, obviously, right? Okay. Moreover, if you think about backups and incremental backups, or also cloud snapshots, which are also incremental, imagine this page, and they are on block size, right? At block size, right? Or like the first snapshot, anything, which is very beautiful, incremental, or copy on write, anything. This block holds less useful data. And backups, incremental backups also increase in terms of size of delta. Because for million of records, we need more buffers, up to million buffers roughly, like if you think about it. Or when we have less bloat, each block, each page deliver like whole stores more useful data, and updates lead to smaller deltas. And again, I'm talking about
almost free. Backups do not consume anything. It's just
I don't agree with you. I don't agree with you because I see, well, they are almost free. Well, okay, S3 price, for example, in AWS, S3 price, of course, is much less than EBS volume. Okay, let's talk about storage. Forget about backups. I know you're like maintainer of all G, okay, but still, I think this idea is interesting and unexpected that deltas suffer. Let's think about, forget about backups. Let's think about one primary, multiple standbys. All their memory can be polluted because they need to bring more pages to memory when dealing with this index. When Postgres updates, it needs to read those pages because of index amplification. Each tuple update leads to updating of all indexes, right? But also we pay for more storage on all replicas, right? Because you cannot all replicas have always in Postgres have always the same set of indexes. I remember Andy Pavlov was criticizing Postgres for that. I cannot create index on replica. Well, of course, everything is as is, like identical copy, physical replica, right? So we pay for we have n nodes, we have n replicas, we have n+1 nodes, and this costs us a lot of money because disks are expensive.
And VME disks are not free. Absolutely not like backups.
And VME disks, local disks in Amazon, for example, or what, they are included to price of node, right? This is still exotic. Like we talk about EBS volumes, for example.
Also, don't we bump into the fact that we have to go through more pages, we end up placing some share locks on every one of those writes, on every one of those pages, even if we're not going to write it. We have to acknowledge to somebody else that, hey, we're now reading this. And if we're doing that 10 times more often than we need to, aren't we putting just additional pressure on the system overall?
Okay, guys, you convinced me. This makes sense. Totally. This first argument was enough, like, but
that's too much, right? Overconvinced.
Last time, Nick, you was researching, like when someone hacked on this, and no one was going to implement this
Yeah,
ever.
only discussions. I might be missed something because
If it's so critical, as you described it, it's super critical feature. Why no one is working? Every time I describe this to like MySQL maintainers or Redis maintainers or Cassandra maintainers, they are very surprised. You don't merge pages? How it works for you?
We learned at school how btree works. It's like magically balances itself, almost balancing, like n or n+1, like split and merge. But here we have only split. That's weird. But honestly, I stopped being surprised. I spent a few years thinking about transaction timeout. Now you implemented it and it's already in core. Everyone has it. I was thinking, am I right? Like it's strange that we don't have it. So I'm not surprised. I'm not surprised if this surprise happens. Like, so what? Let's just do it.
So why doesn't it exist? First, understand there's a workaround. There's something called reindex concurrently. Okay, so you can reindex concurrently. Why is it becoming more important now? Because the astronomical growth of data is starting to impact how long those reindex concurrently take. And now we want to stay ahead of the curve on this. So anyways, back to you, Nick. Not only size of data astronomically, and we all talk about importance of partitioning because reindex concurrently, this a very bug in 14.0 fixed in 14.4, which like index concurrently or create index concurrently. By the way, I don't know why abbreviation is CIC and RC. It's CIC and RIC. I just saw in hackers many times like this 3 and 2 letters. It's 3 and 3 letters. So it holds Smith horizon. You're right. If data volumes are huge, you are rebuilding one index and you cannot rebuild the 2 indexes on one table at the same time. Unlike without concurrently, you can build multiple indexes on one table at the same time, which is interesting. Anyway, like while you are doing this, if table is huge, you affect auto vacuum on all tables in the cluster, which is bad. So that's why we say let's split to pieces, and indexes are smaller thanks to partitioning. But I wanted to highlight another factor. Not only is currently maybe more important, not big data, but huge number of clusters. We unfortunately lost Andrey. Wow. He had a power outage, but maybe, okay. Yeah, So he said he'll be right back soon. That's cool. Yeah, so number of clusters explode because of AI builders, and we need higher automation. This is my main point. Because big data still like you can find solution, and because big data databases are still pets. You can they are not cattle, right? So pets versus cattle, we don't have like huge number of them. So you can approach with specific solutions, maybe involving like some huge effort, but still it's possible. But when you think about like a lot of databases which are automatically created by AI, and if some of them start to grow like at least 2 terabyte, who will take care of them, of those indexes? Nobody. So that's why like I'm focusing right now on the automated reindexing solution, for not only for btree, but what we started here, it's even better for btree, because merge will make more sense. Like instead of fixing consequences, it's better to fix root cause, right? So yeah, let's hope Andrey will return, because I cannot imagine myself coding that. It's far beyond my C coding capabilities, far beyond. And for me, it's interesting because I'm working with someone who has a PhD in this topic. That's awesome. And then you have the depth of experience in these things and how they like really impact things, which is great on the other hand. So, and then back to what you said. When we learned about this in school, we learned about how to balance the trees. What's interesting is I went back and restudied a little bit of this, and merging is almost the same thing as splitting in reverse.
Reverse order,
Yeah. So it should be handleable. What makes it difficult is you have multiple concurrent other users that are using it. So my concept in some of this is, as I'm thinking about it, and I threw some notes out earlier about this, is that what if we can actually do a merge and make it feel like it's a page split? Right? So if we shape the merge in such a way that we're merging two sets of pages in a way that two adjacent pages, the second page is actually a merge set of a bunch of pages to the right. And we bring those in, and now we treat this as though we split this one from this one. If we use that similar logic, could we get away with it?
Can you repeat?
Yeah,
so Andrey would hear this. Yeah.
Good. So welcome back, Andrey. I was filling the air. So part of what we're talking about here is going back to our original classes in btrees. We understand that we actually normally implemented it to keep a balanced tree, meaning merging and splitting were part of the original design. Postgres kind of left the merging portion out and just did the splitting, and that's fine. This creates the bloat. One of the thoughts that I had was, if we could shape the merging process so that it felt like it was actually a page split, then we could take advantage of the same logic of this page splitting that already exists to help handle the pages. And so the rough concept here is, if I take the leftmost page and keep it static, and then I apply a new right page to that as a leaf page, and I bring in all of these other records from these other leaf pages and I put it here, and then I pretend that I split this page from this page and apply the same logic that has to relink this, could we get away with that? But before we even do that, we were discussing, when you were correcting me or questioning me on simple versus easier, well, how about we start with the simplest case? We have one node in the tree that has 2 pointers to the left and right side of their ranges. And if we take those that have multiple nodes and we compress that down to a single node, so that we actually replace all of that linked list with just one block, and then relink around this using the half dead flag on the other one, so that anyone who's currently scanning, they'll go through all of the nodes, but anyone who does a new scan will actually skip over to this node and skip back to the next one. So my thought process on that was, if we focus on just this one optimization, and it only implies locking this one node at the top, because it's the one that points down, and then we just have to rethread the two sides of the linked lists that list all of the pieces. That process is probably the single most complicated, the bottom piece at this point, and then the lock. Anything else is going to require like a 3-way lock, depending on which way you go. So by doing this one first, 2 things can happen. We actually can see how to make this work, and we could actually run vacuum and see if it picks up the deleted pages effectively. Because once they're unlinked, they're there as extra pages. We may actually have to do something else, which involves linking them to a list of deleted pages. I don't know. We have to discover that yet, how that process is supposed to work, because the current system doesn't really account for unlinking a page, okay, unless it's completely empty.
Yes, we have unlinking a page, and I think we should like tweak it a bit. So we are not just unlinking, but moving little of tuples to the right and then unlinking.
Yeah. So this becomes the question is, do we create a separate whole tuple, a whole block that we then relink into the mix, and then, obviously change it so that this parent just links to this one block, and then these guys at the 2 furthest ends now link to this block, and the other ones are marked half dead, which was when I read it, the kind of the magic. Or do we use the block in the middle of all of these and migrate data into them? My only concern with that is, if we change the data and replicate any data in the leaf nodes, we run the risk of anyone who's reading those as they're going left to right or right to left. We run the risk that they may see the same records twice because they got the previously completely linked list. And now they get to this page that we have in the middle that we put extra data on. All right.
I also have basic question, small one. Are we going to do it synchronously, like backend when does something, or it will be some background worker or something asynchronous?
Let's see how vacuum is working now. I think we can just extend vacuum.
Actually, yeah, it's a work for vacuum. Yeah.
So here is a function bt vacuum scan. What it is doing, I was recently changing it. So my change was very small. I changed it to read stream, new asynchronous stuff. But basically, it reads all pages through the file in a physical order, not in a tree order. And then for each page, it is doing vacuuming. Vacuuming basically like checking if tuple is removable, and if everything is removed, calling a function that is doing delete. So
delete of tuple or delete of reference inside index?
Delete of whole page. Attempt. So as a result of vacuuming a page, we have this flag attempt page delete. So if we removed all tuples from a page, we will attempt to delete a page. We will just call bt page delete. How it works? Let's see it. It will. I don't know what is it for loop here. It will try to lock a buffer. What is going on here? So it will try to find the parent.
Oh, there's the half dead. You see how it marks it if it's not marked half dead? That was the flag I was talking about setting. But okay, go ahead.
What is half dead? What is it? This is a page that was already was recycled.
No, it's how you flag a page to tell it that you're changing the links that point into it from elsewhere. So what's happening is so as someone's traversing this through the actual leaf pages, once they get and see the flag that this page is half dead, it means that the tree is in the process of being updated. Okay. And you could be reiterating over something if you're not careful. So it's being held there for processes to finish using, because if you're in a linked list, you're in a linked list, but the linked list is about to change. So this is half dead, meaning you can still use it, but in the future, this is gone and they're going to remove it. That's my understanding.
Okay, so basically half dead is not a part of a tree already.
Right. For new transactions, half dead pages shouldn't be really visible because you're already in the process of unlinking them.
Okay, so here we find right sibling and
oh, good. So it'll keep deleting right siblings if they're also empty. If I understand that code, right? So you see how it says if not right sibling is empty, break. Otherwise, it'll keep moving to the right. Oh, that's cool. So if it finds multiple leaf pages in a row that can be deleted, it's going to delete them.
Yes, but I'm not sure that's the exact function that I was like thinking to tweak. Let's see, colors. There is only one color. So I don't see where do we unlink it from a parent in this. So this is a function that is doing vacuum, and it must remove a reference from a parent page. But I don't see this code here.
But didn't you just read through the code that looked for itself in the parent in that for loop? I thought that's what it was doing. Is it was in order to refine the child node, it has to start at the top of the B tree and actually do a proper search, and then it gets to the point that it points to the leaf node, and then it knows that that's the parent. That's what I thought it was doing in that one for loop.
I think you're right.
It's accidentally happened before.
But where do we remove a parent pointer? I don't see it. So this is a scan that is looking for parent parent downlink. We are going to find it and what to do. We are doing searches on tree to descend.
There you
But I
go.
don't.
So slow back down. Come back down a little bit more. Just right there. So see if it's safe to delete this comment right there. See if it's safe to delete the leaf page and determine how many parent or internal pages above the leaf level will be deleted. Okay, so this is actually doing even a little bit more of the leaf node deletion. I wasn't aware of that. If it's safe, then BT mark page half dead will also perform the first phase of the deletion. So remember how I said the half dead gets flagged when it starts the unlink process. Okay. And
Got it.
yes, so that's that part.
So here must be somewhere. Yeah, so we lock a parent here, and somewhere here must be unlinking.
So there you go. btree tuple set downlink, right? That's going to be the one that sets the downlink from the leaf page, from the parent page to the leaf page.
I don't get it.
Okay. Yeah, so that block starting with 2215 to 2223, the way I read that is the subtree reparent that's the beginning of it, and that handles the left-hand side of the page, right? Because the subtrees always start to the left. And then the last piece is the set tuple downlink, and then that handles the right side of the page if that needs to be updated.
Yes, but I was expecting that we will delete a tuple, and instead of deleting, we are changing its downlink. So
yes.
On a parent page, I would expect this code actually. Here we go. Why do we change downlink and then delete the same?
No, notice it's next offset.
Okay, I got it.
Okay.
It's next. We
Right.
deleted, so we shifted downlink to the left.
Yeah, to the left or to the right, technically, but yes, we shifted it, and now we can delete.
And deleted tuple which we shifted, downlink of which we shifted.
Right. So we linked further to the left than before because I have a page here that's being deleted. I was pointing at it. Now I have to point one page to the left and delete the one that's next. Right?
Oh,
So if I was pointing to the one that needs to be deleted, I actually have to point one to the left of it, and then I have to delete the one that's to the right of that one. The next leaf page is the one that gets deleted.
okay, P offset is left page that will be offset of a downlink of a left page which will be deleted. Next offset is a downlink is an offset of a tuple that is pointing to right sibling of page that will be deleted.
Okay.
And we are reusing old tuple of P offset of left tuple to point to parent, to point to right sibling of page being deleted. Why don't we just delete this P offset? Maybe there are some comments about it. I need to draw it actually.
Yeah, that would probably help. But I'll read out loud the comments, right? Update parent of the subtree. So in this case, it's updating the parent of the subtree. So this isn't dealing with the leaf. This is actually doing more than we were talking about. This is collapsing. This is actually technically doing a merge on the tree portion. So we want to delete the downlink to the top parent and page root of the subtree and the following key, okay? Easiest way is to copy the right sibling's downlink over the downlink that points to the top parent page. Then delete the right sibling's original pivot tuple. And then the next paragraph, the Lannon and Sasha make the key space move left when deleting a page, whereas the key space moves right here. Okay, so they're actually admitting they're moving the key space to the right. That's why we cannot simply delete the pivot tuple with the downlink to the top parent page. See the btree README. That I think answers your question.
I got it. So the downlink tuple effectively is a key that is the left part of a key space of a referenced block, referenced page.
Yes.
It's not right, it's left. That's why we have to keep key of deleted page and use offset of right sibling of deleted page. Okay, now I hope I understand it. Okay,
Well,
now I misunderstand it less.
good. So I'm going to raise it. You made a suggestion. Hey, why don't we just do all of this work inside of vacuum? And I want to raise the red flag that what I don't like about fixing it inside a vacuum, okay, is that it gives us far less control and it's a much more complicated thing. Since we know vacuum will remove deleted pages that are no longer referenced, I was really hoping we would just focus on how to create empty pages that vacuum will be happy to delete for us. So we could just have our command process at first. Now, later, if you want to move this logic into vacuum, sure. But I figured it would be a lot easier to debug if we could actually run our code and check out the resulting structure before vacuum works. Because the problem is once vacuum runs, it's opaque. And what it deletes and what it moves around is going to be a lot more complicated to find. Whereas if we run our code, which looks for the bloat a certain way, we could run a double check that says, oh, look, the number of leaf pages that are linked are 10 times less, the number of this or that. So just from a debugging and logically working this complex stuff out, I was going to leave the migrating of the data and compressing the data into fewer leaf nodes and relinking them only up one layer to us, and then let vacuum go through and clean out the bloat, because those pages are either no longer referenced, right? Or those pages, they're completely empty and can be deleted. Because I think that's an easier problem to solve, but I'm open. Like, I'm just throwing it out there.
This is a place where we are going to attempt to delete a page.
But
What
it
if
will only attempt to delete the page if the page is already empty. So the challenge is that there's only one row on it. How do we fix that? But go ahead.
What if we move here so we see that we have not so many tuples here. First, somehow we know that on the left page from here we have enough room to fit our tuples, and we just move all tuples to the left page from here, and then just raise this attempt page delete flag. Is it a correct way to? Does it?
Secondary problem, you have transactions. And so if the vacuum is running inside of a transaction so that it can be undone if it gets interrupted, the challenge is okay, good.
No, it can't.
So the problem is if this change is forcibly visible enough, like, does this make the change safe enough to make if we do it both at the same time? Like, before we finish vacuuming this page and delete it, and before our vacuum finishes, will every other reader in the system see this change? The move left.
I think the problem with the move left is that we actually have to, like, split is moving tuples to the right, not to the left. If someone is descending by downlink from a parent page and see no tuples by scan algorithm, they can only continue searching to the right. They never follow left from the page. That's why if we are moving something, we have to move right here.
Okay. I would agree with that based on how this appears to be documented.
And if we ever move anything to the right and adjust our high key, probably we won't violate much of invariance here. I hope so.
And that's kind of what I was talking about when I said if we can make the page merge feel like a page split, we can take advantage of the algorithm that they already have. And that was kind of anchoring the left page and changing the right page as that approach, because that's how we kind of split pages. And if the end result is a new page that's to the right of the leftmost page that contains many pages worth of data that we pulled over, as long as the change we make is to the right relative to this pointer, the question is, for somebody who's traversing the tree in reverse in descending order, they're traveling down that node and then they're walking backwards through the leaf nodes. Okay, they will grab those links in reverse order.
I'm trying to find NB split BT insert probably split.
I'm sure the word split has to be there somewhere, no?
Yeah, here is a split of page. So we are doing finding split location, so just picking a pivot tuple for splitting.
And I read this. This is actually a little more complicated than most people would pay attention to. When you split the pages, you have to have room for the two sets of tuples you're splitting plus the tuple you're inserting. Okay, so you got to keep that in mind because you could choose a split between two pages that didn't leave you enough room in either side to put the extra tuple. So tuple, however you want to say it.
Yeah. So we are making a new left page. So and we are effectively trying to reverse split.
Yeah.
Right. Is it? I'm reading the paper right now. It's two-phase, right? So that's where half-dead term came from.
Exactly.
Are we going to invent the term half-life or something?
No, let's
Originally, Lan and Shasha, they say half split and half merge. So half dead. I think it's variation of that for Postgres.
So, yeah, I'm wondering if it should be. Yeah, it could be half live. How about almost healthy?
Half healthy. So it's two-phase. I'm trying to map what you're doing here to the paper.
So do we need some new state for like?
Well, yeah, this is the hard part to think about, right? When you think about why they had to use half dead, is because it's the two-phase aspect. They make one set of changes, they mark it so that everyone else knows that this is going away, but you can finish your search and your queries for the existing one. And then the flip side is once you're unlinked from there, you're all dead. Now, I don't know if they change the status after that, or if they just leave it and it's now unlinked, and that's what made it like all dead, kind of thing. So, but it was the previous path is broken in a future query.
Okay, so if we are just attempt here to move everything to right page, can we just ask cursor to do so? We need a condition to do it. So
I think if we use our own code, it'll be easier to ask cursor to write the logic. Just like we already have the code snippet that calculates how much bloat there is.
the thing is, the code that is written is a logical traversal. But here we have physical traversal. We are not reading left page and right page. We are reading page number 7 and then page number 8. And they might be not related at all.
Well, that's
So
okay, because what I'm looking for this solution is I want it to traverse the tree, right, and get down to one node above the leaf nodes. And I want it to find where the left and the right pointer are not pointing to the same page. Okay.
we can build some in-memory structure that says say hash table from block number to empty space. If we visit, so if we know that right page have room for our tuples, we move everything to the right. Does it make sense?
Yes, but explain to me, hold on, explain to me how you treat a current running transaction that started at your left page and it already went through multiple pages that we collapsed to one to the right. And then it gets to that page. We have to avoid it transitioning ever to that page, right? Because it'll reprocess the exact same records it already processed.
We will lock them together. We will lock left and right page, both. There might be someone who read.
Right, write it into memory, and they're going to process. And then when they're done with that, they're going to go to the next page, and they're going to end up rereading the same exact tuples they've already processed. This is the nuance.
I don't know what to do with it, actually.
So and this is where I'm asking questions I don't know, right? My PhD, I don't have, and it's not in this. So the question is this a valid use when we start this process where we copy those records over to your extra page? Okay, and I'm going to call it an extra page right now. We allocate an extra page. We copy those tuples over, and then we do the magic of marking the previous links half dead, starting from where we started removing the tuples. And then we change the pointer that pointed to this link to point to ours instead. And then we fix the right-hand side to be doubly linked so it can be reached backwards because it's a doubly linked list. Can we pull that off? Will that work? So
all that work about unlinking page is done in this if statement. We just need to move tuples to the left, to the right, anywhere.
okay.
Here.
So the only way it works then in my mind is if the transaction ID is slightly different for these new tuples. They're treated like copies of the
Kirk,
original.
this system, indexes system, is lower than transactions. It doesn't know anything about transactions. It's transactions that have to know about the system.
Okay.
So
All right,
it is residing over storage manager and wall login manager, wall login subsystem, but it have no transactions. All the things that we have to guarantee that each scan will see every tuple and see it only once. This is
that's the problem.
that's
See it
all
only
what we
once.
guarantee. Yes. Actually, I don't think it's a big problem. Let's see. Here is a left page and then right page. And also there is a parent page that is linking to
The left
to
and the
to
right.
to 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 to, to left. When we are grabbing logs, we log left page here. Then we log right page. Right page. Move all tuples from left to right. Here it was 1, 2, 3. Right page. Oh, how do I accept it?
A tab.
Yeah. So we moved these 3 tuples here. If the transaction was observing left page in this state, it cannot follow to right page. So we are picking logs together on the left page and on the right page. We are coupling these logs.
Okay, so we're going to lock the left and right page at the same time, basically,
Yes.
as close as we can. Then we're going to copy the data from the left page to the right page.
No, I'm wrong. The reader is reading left page, observing 1, 2, 3, then releasing log from left page and starting to read right page. And hence, at this moment, we will do our business by locking them both, left and right. Move tuples here to the right page, and then reader will wake up and sees 1, 2, 3.
Again.
Again, yes. Mm. The thing is, my PhD is in geospatial indexing in our trees and
Come
gist.
on, come on.
I don't
It's
know how it should be solved. I've read the paper of Lanin and Shasha, but I don't know how do they solve this problem?
So this is, again, this is part of why I felt the best thing we could do is we have to solve this problem outside of the vacuum problem and then leave empty pages, and vacuum will handle it naturally. But this is the hardest part of this process. So now tell me, from your understanding, how does the page split work when it splits 1 through 6 into 1, 2, 3, 4, 5, 6?
So we have parent page
Missed
1.
five.
It's missed. It's missed for a
Oh,
reason.
I see.
So we are going to insert it, and that will cause a page split.
Mhm.
We will create a new page here with 1, 2, 3. Remove this. Edit here. And then eventually no, it can't work like that. That's what I've read. So new page should be right page, not left page. And then we are adding here a key for the right page. This is a separate change. So the problem is when the reader was looking for key 6, read downlink 1, and is visiting left leaf page, they see that high key here is 3, and they were interested in 6, so they must visit left page 2. In our case, we have opposite. So when we land on the right page, we should understand that we already saw 1, 2, 3. How do we understand that this case already are visited?
And this is where two phases, let's think in two phases. What happens if we move the 4, 5, and 6 to the right, okay, and we mark the rightmost page half dead, leaving it at 4, 5, and 6? So that somebody who started reading before we got our lock at 3, someone who started reading, read 1, 2, 3, they move to the next page, they see 4, 5, 6. But the next person who reads the leftmost page will see our 6 in the rightmost spot, as well as the 4, and 5 will be there. And then when they get to the next page, they're going to see the half dead marker, right? Because we're going to have to mark the right page half dead in order to indicate that as you came in, you might have to make an adjust.
I thought that we will mark half that left page.
Yeah, but
Or
okay.
okay, if we are moving 4, 5, 6 to the left, this problem is much easier.
Mm-hmm. Yes.
This is half that. They visit half that page, and they understand that they have to visit left page.
Or they have to understand that anything they process could be a duplicate. Like this is their chance to remove the duplicate. I don't know if that's in the current logic for scanning the index, but if it is, then this will technically solve the problem.
I don't think it's there.
I'm going to make a note so we follow up on that.
So, let's get back. So first we start with removing downlink. I got it. So we have to remove downlink before we move any tuples between these pages. So this page must be marked like it is half merged, and that is half merged. No, just this is half merged. So that scan is aware that it might see 1, 2, 3 here when the scan lands here. So it's not that easy. We cannot just move it. It's a two-phase algorithm. First, we must remove a parent downlink, and only then move anything between pages. And we will have to make sure our scan algorithm is aware of half-merged pages.
And so that's why I captured the note. We have to study how the index scans work with half-dead pages, because once we know that, then it may answer our question for flagging these as either half-dead or half-merged. I would not like to introduce a new concept just because the amount of code it could potentially have, but we may be forced to.
So scan. Just a moment, I will find the scan code. It's not that difficult actually. NBT scan, begin scan. And this is all setting up. And I don't see actual work here.
Hold on. If scan key and that number of keys is greater than 0, okay, that's fine. Keep going. BT scan position is valid. That seems like. We have to kill with any killed items. The 4 leaving the current page deal with any killed items.
That's another cleaning technique. That is when we are scanning btree and observe some dead items, we are killing them without actually waiting for vacuum.
Okay, so we're kind of marking them really dead.
Yeah, for us, it's just a noise here. It's not what we are looking for.
Cool.
Where is the logic of a scan? It's all in btree.
Should be recursive.
Yes. It should be recursive, but it should be while loop, because Postgres folks do not like recursion because sometimes you just don't have enough space on a stack.
Stack memory. How?
That most of the time they just do palloc of stack and the while loop.
There you go.
Yeah.
There's your palloc.
Where?
1, 2 lines up to the top. A couple more up. Up. There you go. Right there. 453. Scan want tuple 450 line 453. Down a few 453. There you go. There's a palloc right there. What's it doing? It's doing the search object, current tuples, Is a pal, look at the block size time too.
Uh-huh. Hmm. I think it's allocation for a result, not for a stack. Let's just search for a stack. There are no stacks in this file.
How about searching for while? That looks like what you described. Oh, Andrey dropped off with I hope his battery didn't die on him.
Again? Oops.
I don't. At least the screen is still visible.
I think it will disappear in a moment. Yeah, I'm surprised, Kirk, how like you are well prepared today. So you are basically leading. That's great. Thank you.
Oh, my pleasure. It's so exciting to, like I said, to be working with, someone whose PhD is in this topic. And at the same time it's a complex problem. So, but my pleasure.
Basically,
Yeah, go ahead.
I'm also surprised that source code is mentioning Lanin and Shasha paper, but obviously not implementing fully. We just saw it, right, on in a comment. So basically, it mentions it for full, when page is fully empty to get rid of it and rebalance, right? But there is a gap, a lack of proper merge, right? Yeah, that's why I was checking our understanding, and understanding is right. So there is a gap. I still don't understand why there is a gap. I found some blog post quite well in detail describing benefits of Postgres btree implementation, mentioning this paper as well, algorithm as well, mentioning everything but lacking word merge. So yeah, looks like a gap, but yeah, maybe we don't know something.
The other word is rebalance besides merge. So sometimes they'll mention rebalance, but yeah, it strikes me. Here's the great part. At least they told us they're using the same source we are, right? They're telling us where they got some of the original ideas. Right. This means some of our stuff should apply.
Yeah, exactly.
And I'm excited. Again, I want to keep it separate than from the vacuum. And the reason I'm pushing so hard on that is I really think it's easier to test if it's not part of vacuum. And not only that, it's easier to prove. And then there's three different cases. The three use cases I came up with are you have one last tree node that points to two different sets of a different chunk of many blocks in the leaf node range. And reducing that to one single leaf node should be simple. Okay. And if we do that repeatedly, we can get some bloat removal.
I guess I understand. Like if it's a part of vacuum, it might make vacuum very slow, affecting its other duties, right?
And not only that, since vacuum already handles all the page splitting, it actually has a way of merging. Technically, vacuum seems to say that it can do a little bit of merging in the vacuum. The reality is the leaf pages have to be completely empty for vacuum to do that.
Right.
And if that's the case, guess what we can create? We can create empty leaf nodes.
Right, and leave it on shoulders of vacuum to clean up, right?
Which is well tested. Plus, I think it'll be, if you want to talk about getting it through the Postgres people, right? Getting them to accept the patch, if it's a standalone piece that does the work and vacuum does this versus if we modify vacuum.
Yeah, that's interesting. Yeah. So yeah, basically much less to implement if we just need to move references from one page to another properly. That's it. Sounds
exactly. And if we can work that handshake out while multiple things are scanning the index, right? If we can work that out with multiple things scanning the index, and we can make that piece work.
This amazes me even more. So the year of this paper is 1986. The next year it will turn 40, right? And yeah, it amazes me even more. So we talk about split already moves references from one page to another, but it also split needs also create new page. Here we can just move tuples from one page to another, maybe in the same manner, and leave this page empty, vacuum will take care of it. It sounds like easier than split.
Yeah,
right?
well, if you
But
so
why
this is
during
this,
decades it wasn't implemented? So crazy.
sometimes someone just doesn't think outside the box for it. But watch this. What you just said was key about split. Split
Yeah,
creates a new page.
yeah.
That's why I'm thinking to do a merge, we create a new page to put all the data onto, and then we link it in, and then those can stay half dead until they're deleted. And now our merge works a lot like split because we created a new page, but now we just forced our tree to acknowledge only our new page and forget about the old page. And
But
now that
this
doesn't
is
create
different.
the problem where we have to worry about telling the index scan not to scan our page again or not to scan the same tuples we merged.
Well, this
That's
is
why I
different
was thinking
from
that way.
what the paper describes, right? This is different. There is benefit because we don't touch all those pages, but there is also downside because creation of the merge will behave slightly like split because new page created can cause rebalancing as well, right?
It shouldn't because it's a leaf page. So and we're actually we're always doing the following.
But what if?
We're taking a set of leaf pages and replacing it with one leaf page. And we're only affecting one node in the first pass.
Oh,
So we
okay.
only care about the one node that points to multiple leaf pages. We compress
But
those. There's
this,
more ones we can do later, but if we master this one, I think it gives us the experience.
but parent page might not have enough space for link to our page.
Oh no, because the parent page already, let's do this. So this is the parent page. It points to leaf page 1, and then on the right side, it points to leaf page 10.
Okay.
Okay, right? And what happens is we realize we can put all of those records on a single page. So we create a brand new leaf page, okay, call it 11 or 10A. We create this page and we change the left pointer to point to the left of this page, right pointer to point to the right side, or the right marker high water indicator. It's a different thing than a pointer sometimes, to point to the rightmost high value of this page. And those are the two pieces that change.
I don't
Now,
get one thing.
okay.
Yeah.
Which thing?
If we are going to leave actual cleanup of empty pages on shoulders of vacuum or auto vacuum, it means that temporarily those references should be those empty pages should be present in parent page, right?
No, because here's the deal. What we witnessed in this was that the vacuum process scans the entire file. It doesn't just follow the tree. It scans the entire file. So once we link our thing in, then we mark all of these pages half dead that are between these two
Sounds
links.
good. But what if it's not 10, but already this like maximum number of children a parent page can have?
That's okay. We reduce it now. Maybe we reduce it to 2 parent children, right?
Okay.
From
I
whatever
still
number.
I'm detached from code too much. In my head, in some abstract btree, I still like don't fully understand. Anyway, Andrey is back. That's great. You are muted.
You're muted.
Yeah, I got my power back. Sorry for
no
this
problem.
restarts.
No problem.
We were looking in the
Share your
wrong
screen.
place. Just a moment. The thing is, like, we were looking for usages of half dead. That's not a transition state that we were looking for. We are looking for transition state, which is a half split.
Ooh.
So we want to unsplit page. The part that is unlinking empty page is already there. We want to undo distribution of tuples between 2 nodes. And this is work that is done by a function finish split. So when we are splitting page, we are starting with distributing tuples between two pages, and then finishing split. And so now we have to unfinish split, like finish split back. I don't know how to say it. And then then we can move tuples as we want.
Okay, so this is technically would be called finish merge. The opposite of
Yes.
split is merge, so finish merge. So we need to review
Not
start
finish.
split and finish split.
That was finish split, and we want start merge.
Okay, and start merge.
We have to reverse them both. So we want this function to be the effect of this function to be undone. And effectively, it's inserting downlink and marking something on pages.
See the rightmost page? That was what I was talking about. That's the other side, is that the parent contains the rightmost indicator too.
I don't. So we have left buffer, right buffer.
Oh no, line 2279, just a couple lines above you. There's a leftmost L page op and a rightmost R page op on that line. So those constants, those all uppercase stuff. Was this the only page on the level before the split?
This means like if it was the only, that means we will have to have a new root page.
Okay, yeah, that's a new root check. Got it.
And adding new root is opposite of descending tree. That's what we are not going to have anyway. We might consider it later, but so far there is a lot of stuff to understand yet. And effectively, we want to remove this insertion and also mark something pages so that scan can understand that these pages must be processed in some clever way. And actually, I don't know what to look for. I just have to understand all this exact function. I was like saying that this time we will be mostly hacking. It seems like I was wrong. It actually is more like podcasting. But that just hard topic. Now I see why it's not why it wasn't implemented for a long time. So maybe let's wrap up for today, and I will have some homework to understand how this should work.
Yeah, let's offline it too. Bounce some things off of me, because I'm really curious about how we can actually make this happen. But I think it's doable. But I could just be missing it could be the horizon effect. The real problem is the piece after I have to open the magic box.
Yeah, maybe there's a big roadblock here, right?
Right.
Okay.
But the reality. But if we compare it to a split, it's close. It's close. I'm almost willing to split. Here's the deal. I'm almost willing to split the data by adding a blank page, then our merge data, then another blank page. And the reason for that is because I know vacuum will clean it all up. But if that makes it feel more like a split, then I'm happy.
Yeah. Andrey, did you understand this idea of Kirk? Yeah?
Yes, but
third page, basically.
I understand, but
not well. Your gut tells you something.
Yes. I feel there is some problem with it, and this is exactly the same problem that we are dealing with, just merging two pages instead of merging two pages into one. Into one third page, and I don't fully understand what's the problem actually yet. I just have intuition that it's the same problem, but not real understanding.
All right, we'll take it offline. Excellent session, though. Good discussions. And you know, for those of us, or for those following along, yeah, these are the complexities. It's not trivial. This is not a trivial, you know, fix. And you know, the approach you take matters. And the other thing that I've learned over the recent, you know, year or so of doing this with you guys is we also have to be able to sell the final solution to the Postgres group.
That's true. That's why I'm trying to extend the code, not change everything.
Right. Awesome.
Great. So thank you. Baby steps. I hope, yeah, next time we will do something else. Yeah.
Thanks, guys. We will finish it one day.
Yeah. Have a great rest, Andrey, as well. Yeah. Thank you. Bye.
Excellent.
Bye.